Download this code from codegive.com, link in the description below. A comprehensive tutorial on Go's Go/analysis framework, building and using a custom analyzer. Go's Go/analysis package provides a powerful framework for building static analysis tools, often referred to as analyzers, that can inspect Go code for potential errors, stylistic issues, performance bottlenecks, and other problems. These analyzers can be integrated into your development workflow to improve code quality, enforce coding standards, and detect bugs early in the development process. This tutorial will guide you through the process of creating and using a custom Go analyzer. 1. Understanding the Go/analysis framework. The Go/analysis framework revolves around the following core concepts. Analyzer. The heart of the system. An analyzer is a struct that defines the analysis to be performed. It specifies the types of information it requires, example abstract syntax trees, asts, type information, the logic to analyze the code, and the results it produces. Pass. A pass struct represents the context in which the analyzer operates for a specific package. It provides access to the parsed Go code, asts, type information, and other resources needed by the analyzer. Think of it as the environment the analyzer runs in. Result. An analyzer produces results in the form of analysis.diagnostic structs, which represent findings in the code. Each diagnostic typically includes a position in the source code, a message describing the issue, and potentially suggested fixes. Run function. The core analysis logic resides within the run function, which is a method on the analyzer struct. This function is invoked for each package being analyzed. Fact. A fact is information derived from analyzing code, that can then be used by other analyzers. Facts are package specific. For example, an analyzer might determine which functions within a package are pure, i.e., have no side effects, and expose that information as a fact. Other analyzers could then use this fact to, say, detect potential issues when a pure function is called but its result is discarded. Unit of analysis. Analyzers typically operate on packages. The framework iterates over all packages in the analyzed code and invokes the analyzer's run function for each package. 2. Setting up your environment. First, ensure you have Go installed and configured properly. The Go/analysis package is part of the standard library, so you don't need to install it separately. Next, create a new directory for your analyzer project. 3. Defining the analyzer, the analyzer struct. Create a file named analyzer.go in your myanalyzer directory. This file will contain the definition of your analyzer. Explanation. Package main, this is crucial. Analyzers intended to be run via the command line need to be in the main package. Analyzers meant to be part of other analysis workflows, example in a CI/CD system, might be in a different package. Analysis.analyzer, this is the core struct defining your analyzer. Name, a unique name for your analyzer. This is used to identify it when running analyses. Choose a descriptive name. Doc, a documentation string that describes what your analyzer does. This is important for users who will be running your analyzer. Run, this is a function that performs the actual analysis. It's the heart of your analyzer. We'll define this later. Requires, this field specifies the other analyzers that your analyzer depends on. The Go/analysis framework will ensure that these dependent analyzers are run before yours. Here we require the inspect analyzer. 4. The run function, the core analysis logic. Now, let's implement the run function. This function will receive *analysis.pass and perform the actual analysis on the package. Explanation asterisk. Asterisk pass analysis.pass, the pass variable provides access to information about the package being analyzed. Crucially, it includes the AST, abstract syntax tree, representing the code. Asterisk pass.result of inspect.analyzer.inspector.inspector, this accesses the results of the inspect analyzer, which we declared as a dependency in the requires field. The inspect analyzer provides an inspector, which allows us to traverse the AST in a controlled manner. We need to type assert the result of pass.result of to the correct type. Asterisk inspect result.preorder, node types, func, and ast.node. This uses the inspector to traverse the AST in a pre-order fashion. Node types specifies which types of AST nodes we're interested in. The anonymous function is called for each node of the specified types that is encountered during the traversal. Asterisk switch n equals n, type. This is a type switch. It allows us to handle different types of AST nodes differently. In this example, we handle ast.ident, identifiers, and ast.basiclit, literals. Asterisk log.printf, prints out information about the identifiers and literals found. You'd replace this with your actual analysis logic. Asterisk pass.fset.position, n.pos, the fset, file set, maps positions in the AST to line and column numbers in the source files. This is essential for reporting errors accurately. Asterisk return nil, nil, the run function must return two values. Asterisk the first value can be used to pass information between analyzers. If your analyzer produces a fact, that would be returned here. In this simple example, we don't produce any facts, so we return nil. Asterisk the second value is an error. If the analysis encounters an error, it should return a non-nil error value. In this example, we don't expect any errors, so we return nil. 5. Reporting diagnostics, finding and reporting issues. Instead of simply logging to the console, we want to report findings as diagnostics so they can be displayed by analysis tools. Let's modify the run function to report duplicated nodes, even though it's contrived for this example. Explanation of the changes asterisk. Asterisk scene nodes equals make, map ast.node bool, a map to track scene ast nodes. Asterisk if scene nodes n. If a node is already in the scene nodes map, we consider it a duplicate for demonstration purposes. Asterisk pass.report, analysis.diagnostic. This is the crucial line. It reports a diagnostic. Asterisk pos, n.pos, the position in the source code where the issue was found. Asterisk message, possible duplicated node found, a descriptive message explaining the problem. 6. Creating the main.go file, running the analyzer. Now, create a main.go file in your myanalyzer directory. This file will contain the main function, which is responsible for invoking the analyzer. Explanation asterisk. Asterisk single checker.main, analyzer, this is the simplest way to run a single analyzer. It takes your analyzer struct as input and handles the command line parsing, package loading, and execution of the analysis. 7. Building and running the analyzer. Now you can build and run your analyzer. The go build command compiles your analyzer into an executable named nodedupe. The /nodedupe/ command runs the analyzer on all Go packages in the current directory and its subdirectories. 8. Testing the analyzer. To make your analyzer robust and reliable, you should write tests for it. Go/analysis provides a testing framework specifically designed for this purpose. Create a directory named testdata alongside your analyzer.go and main.go files. This directory will contain Go files that your tests will analyze. For example, create a file named test.go inside the testdata directory. Now, create a file named analyzer_test.go in your myanalyzer directory. Explanation *analysis_testdata. This function locates the test data directory and loads the test cases from it. *analysis_run, test data, analyzer, test data. This function runs the analyzer on the test cases in the test data directory. It expects that for each file in the test data directory, example test.go, there is a corresponding file with the same name and the suffix .go.golden, example test.go.golden. This golden file contains the expected output of the analyzer. If the actual output of the analyzer doesn't match the content of the golden file, the test will fail. To run the tests, use the go test command. Creating golden files. Initially, you won't have any star.go.golden files. When you run go test for the first time, the tests will fail. The output will tell you that the golden files are missing and will provide the actual output that was generated. You need to create these golden files manually. For each file in your test data directory, create a corresponding file with the .go.golden suffix. Paste the expected output from the go test command into these golden files. For our example, the test.go.golden file should look something like this. The exact line numbers might differ. After creating the golden files, run go test again. This time, the tests should pass. 9. Adding suggested fixes. Analyzers can provide suggested fixes to the issues they find. This can greatly improve the developer experience by allowing them to automatically correct the detected problems. Let's modify the analyzer to suggest renaming duplicated variables to be more distinct. This is just an example. In reality, you'd provide more meaningful fixes based on the specific issues your analyzer detects. First, modify the analyzer.go file. Explanation of the changes *** suggested fixes, analysis.suggested_fix. We add a suggested fixes field to the analysis.diagnostic struct. This field is a slice of analysis.suggested_fix structs. *analysis.suggested_fix, this struct describes a potential fix for the issue. *message, a message describing the fix. This should be clear and concise. *text edits, a slice of analysis.textEdit structs, which specify the actual changes to be made to the source code. *analysis.textEdit, this struct describes a single text edit. *POS, the starting position of the text to be replaced. *end, the ending position of the text to be replaced. *new text, the text to replace the existing text with. In this example, we're simply appending _new to the identifier name, which is a very basic, and potentially incorrect, fix. In a real analyzer, you would need to be much more careful about generating valid code. Similarly, we change literals to 11. Updating the golden files. Because we've added suggested fixes, we need to update the golden files. Run go test again. The tests will fail, and the output will show you the new output, including the suggested fixes. Update your star.go.golden files to include this new output. The test.go.golden file should now look something like this. Running the analyzer with fixes. To apply the suggested fixes, you can use the go tool fix command, but first, you need to install the static check tool which provides the fix flag. This command runs the static check tool, which includes your analyzer, on all Go packages in the current directory and its subdirectories, and automatically applies the suggested fixes. 10. Creating and using facts. Facts are pieces of information that an analyzer can derive about a package and expose to other analyzers. This allows analyzers to cooperate and build upon each other's results. Let's create an analyzer that identifies functions that only use variables defined within their own scope, pure functions. A second analyzer then leverages this fact to determine when these functions are called but their results are ignored. Asterisk define a fact type asterisk. Create a new file called pure.go. Explanation asterisk. Asterisk type pure function struct functypes.func, defines the pure function struct. This is the type of fact that our analyzer will produce. Asterisk fact types, analysis.factNew, pure function, this is crucial. It tells the Go/analysis framework that the pure analyzer produces pure function facts. The Go/analysis requires the fact types to be initialized using new. Asterisk pass.export object fact, f, new, pure function, this is how the analyzer exports the fact. The first argument is the object, in this case, atypes.func representing the function that the fact is associated with. Asterisk consume the fact asterisk. Now, create another analyzer, in a new file called useless_result.go, that consumes the pure function fact to check for useless function calls. Explanation asterisk. Asterisk requires, analysis.analyzer inspect.analyzer, pure analyzer, the useless result analyzer depends on both the inspect and pure analyzer. This means that the pure analyzer will run before the useless result analyzer, and its results will be available. Asterisk pass.import object fact, fn, and pure, this is how the analyzer imports the fact. The first argument is the object, in this case, atypes.func, that we want to check for a fact. The second argument is a pointer to a variable of the fact type, pure function. If a fact of that type exists for that object, it will be stored in the variable. The function returns a Boolean value that represents whether a fact was successfully imported. Asterisk if pass.import object fact, fn, and pure, if import object fact returns true, it means that the function fn is a pure function, as determined by the pure analyzer. We can then report a diagnostic if the result of the function call is discarded. Asterisk update main.go asterisk. Modify main.go to include both analyzers. Now we use multi-checker.main instead of single checker.main to run multiple analyzers. Asterisk update test data and analyzer_test.go asterisk. A similar approach to the original analyzer testing needs to be taken here. However, the analyzer output now needs to contain the result of running both analyzers. Testdata/test.go. Analyzer_test.go. Testdata/test.go.golden. Important notes about facts asterisk. Asterisk performance asterisk using facts can improve performance by allowing analyzers to share information and avoid redundant computations. Asterisk communication asterisk facts provide a structured way for analyzers to communicate with each other. Asterisk evolution asterisk you can add new analyzers that consume existing facts without modifying the analyzers that produce them. Asterisk scope asterisk facts are package specific. A fact produced for a function in one package cannot be directly used by an analyzer operating on a different package. Asterisk dependencies asterisk be careful about creating circular dependencies between analyzers. If analyzer A depends on analyzer B, and analyzer B depends on analyzer A, the Go/analysis framework will detect this and report an error. 11. Deploying your analyzer. Once you've created and tested your analyzer, you can deploy it so that others can use it. There are a few common ways to do this. Asterisk as a command line tool. Asterisk the simplest way is to provide the executable as a command line tool. Users can download the executable and run it on their code. Asterisk integrated into a CI/CD system. Asterisk you can integrate your analyzer into your CI/CD pipeline to automatically check code for issues during the build process. Asterisk as part of a larger analysis tool. Asterisk your analyzer can be included as part of a larger static analysis tool, such as static check. 12. Conclusion. Go's Go/analysis framework provides a powerful and flexible way to build custom static analysis tools. By understanding the core concepts of the framework and following the steps outlined in this tutorial, you can create analyzers that improve code quality, enforce coding standards, and detect bugs early in the development process. Remember to write thorough tests and provide helpful diagnostics to make your analyzer as useful as possible. The inclusion of facts provides a well-structured and maintainable manner for analyzers to work together to catch complex patterns in your code bases. By leveraging facts, you can build increasingly sophisticated tools.